Alright, I think we're back. Yeah, I'm sorry guys, my computer just started glitching out for a second, so I had to restart it really quick. Hopefully we don't get another glitch. So I'll just be splitting these into two videos, I guess. So we'll move on with this one right now, fluids. So first off, I think with hydrostatic fluids, the most obvious thing we should talk about, let me give myself some bit more room, would be density. Density, it's written as D. It can also be written as like a really weird like P shape. You'll see as P, but I prefer the D. No worries though. It's basically mass over volume. Another topic I want to talk about would be topic of weight when it comes to fluids. So weight is basically is equal to pressure times gravity times volume. And speaking of pressure, pressure is force over area. Absolute pressure is just the fluid's pressure with respect to gravity. Gauge pressure will be basically just pressure of gravity minus the atmospheric pressure. I'm trying to think of other stuff I can talk about. Specific gravity, let's talk about that. That's basically just the substance's, the density of substance. These all look like P's, I'm sorry. I'm going to make this a D. I know it's written as like a weird P variable, but you guys are getting a D, because I can't tell the difference. So, density of a substance over the density of water. Or basically any substance, but usually it's water. Density of whatever you're given over like the larger object. There's no unit for that, by the way. I just want to point that out. The density of water is 10 to the third kilograms per meter. Make sure you know that. That's like obviously a universal. I think you have to know that. Let's go with the continuity equation. Continuity equation states that A1 V1 equals A2 V2. So the area times the volume of one fluid should be equivalent to the area, and it's basically a direct relationship, or an inverse, sorry. Bernoulli's equation is density. Sorry, not density, pressure. Pressure plus 1/2 dV squared plus dGH. That equals a constant. That's Bernoulli's equation. Now, with that being said, let's move on towards Archimedes' principle. I think my little like HUD stuff is being like blocking you guys here. Archimedes' principle states the buoyant force is equivalent to the weight of the displaced water. So it'll be written like as an equation, it'll be like F buoyant force is equal to the density of the fluid times gravity times volume displaced. That obviously is being the weight of the displaced water. If it's displaced, if the weight of the fluid is less than the object's weight itself, it will sink. If the weight of the fluid is greater than the object's if the weight of the fluid that's displaced is greater than the object, it will float. Now, Pascal's principle, this honestly covers it perfectly. If I can have anything to add, I'll probably add it in blue. So any change in pressure applied to an enclosed fluid, its If you had a F1 here, it'll push out F2 here, but it's uniform. If there's anything I can say, it's uniform force. So F1 D1 equals F2 D2. P equals F1 over A1. That's also true. F2, I think. Am I lagging? I don't want to restart this again. I'll just write here P equals F1 over A1 equals F2 over A2. A1 D1 now there's two D's present. I hate it here. Equals A2 D2. This D is distance. It's not density, it's distance. So knowing this, we can say that work is F1 D1 and it's equal to F2 D2. I hope this makes sense. Fluids is really complicated. It's not my specialty either, but I'll try my best to answer any questions if you guys have any. No questions, really? I don't think I did that good of a job explaining it. Alright, well, if you guys don't have any questions, we can move forward with fluids. Wait, it doesn't get any more fun, guys. No, I'm sorry, I won't be negative. We have to learn this. So waves, longitudinal versus transverse waves. Transverse waves are your traditional waves. These are, like, if you ever, like, make an impact on the ground, that's the vibrations that are racing forward. Longitudinal waves are more like sound waves. So these are just traditional waves. I have written here that T is a period. A period is basically just one cycle. So going from crest to trough, basically going from here to here to here again. Undershot a little bit, my bad. To here again. That counts as one cycle, as I've written here. So that also counts as one period. The frequency of a wave is known as 1 over t, so 1 over its period. And the velocity of a sound wave, or just any wave, would be frequency times lambda, which is its wavelength. Let's talk about some pipes then with waves, because when you're traveling waves through a pipe, we need to learn about that. Open pipes, its wavelength, you can determine it by its length over n, which is usually its harmonic. Harmonic being like, if it's like this, or if this is 1, this would be 2, stuff like that. I'd like to point out that this is basically the ends will be integers, so it's like 1, 2, 3 for open pipes. Same thing with its frequency, n equals 1, 2, 3. Going forward, just every integer. Sorry, I just blanked for a sec. Closed pipes. They're a little bit different equations. 4L over n, NV over 4L. So these do not work as just regular integers. They'll be every other integer. So it'll be like 1, 3, and 5 moving forward. 1, 3, 5 moving forward. I think I'd like to, if I drew that again, with strings and pipes in general, waves in general. So the ends, so the ends are known as nodes. But yeah, let's pretend like this part doesn't exist. So these are known as nodes. Nodes occur when displacement is 0. That's why I drew it like when it's at the line. Anything else I want to talk about? Not really. I think I just want to like point out open waves also work like standing waves. That's where like you can just like if you have like a jump rope or any sort of string that you can just like sort of like whip on the ground, that's a standing wave. They work like that. Closed pipes, they're different. That's why you have to memorize a different equation. So yeah. Any questions? Cool. We'll be moving forward then. Circuits. I like circuits a bit more. I won't lie. V equals IR. Most important equation for circuits. V equals IR. Voltage equals current times resistance. Resistance obviously is the opposition of flow to charge. Think of it as like the inverse of current, and so you can see through that equation it is inverse. So as V goes down, resistance will go up, and vice versa. Let's move. I guess we're moving directly forward towards circuits, parallel circuits, and series circuits. Parallel circuits are circuits that have their resistors parallel to each other. Yeah, my computer is all weird today, guys. I'm sorry. R1, R2, R3, these are parallel to each other. They do not touch. I'd like to point out that they've given it to us here. Like the current is basically just you're adding the current up. So I1 plus I2 plus I3 will give you the total current. I don't particularly like the way this is written. If I'll be honest, I'd cross that out. So for parallel, so I total, I guess they have it IS, I'll write IT. I1 plus I2 plus I3. The resistance will also be the same. R1 plus R2 plus R3. Now with that being said, total voltage will be the exact same as well. It's just simple addition. Parallel ones are the easy ones. Series are a bit more complex. I'm also going to erase this for a sec. You have the resistors in series, as in you go through one in like sequentially. So you should go through R1 first, then R2, then R3. So it's a bit different. I'll start with I's though. So series, it's still going to be I1 plus I2 plus I3. And V is still going to be V1 plus V2 plus V3. But since you're having it in resistors in series, it's a little bit different. It'll be 1 over R plus 1 over R2 plus 1 over R3. If you want to talk about capacitors, it's capacitors. It's the ability to store charge. Why am I writing up? I'm sorry. So yeah, the equation for that is energy stored is potential energy U equals 1/2 QV. You don't have to know this equation if I'm being honest. I think it's just nice to know. And as for capacitors in parallel, they would be just adding it. So CT equals C1 plus C2 plus C3. In series, though, it's obviously not as easy. It's going to be 1/C1 plus 1/C2 plus 1/C3. That's basically all I have for you guys for circuits. I'm trying to think if there's anything else I can add. Unit is amperes. Cool per second. Any questions? All right, cool. Let's move on. All right, sweet. This is the last one we have for physics. Sound and half-lives. That's nuclear chemistry, but I just wrote it down as half-lives. So sound, I basically have everything written down for you guys. Sound, it propagates through the formal medium. Changes depending on what the medium is, but that's something you like. It's kind of common sense. So the level of a sound in decibels, you'll be measuring it with this equation. So 10 log to incoming over outgoing. Though the I's are intensities, incoming intensity over outgoing intensity. For outgoing intensity over incoming intensity, I'm sorry. Unit is a decibel. I like to note that the decibel goes up exponentially, so a 10-fold increase in your decibel will be times 10, but if it's 20, it'll be times 100. Doppler effect. I'll say something about the Doppler effect, guys. So, Doppler effect. So it basically means that whenever a source or a detector, or whenever a source or a detector is moving towards each other, you will hear their frequency differently. A way I like to think of it is when you're standing at a train station, waiting for a train, or a subway, I guess. Like if you're like in New York, you're waiting in the subway, you're just sitting there, or standing there, and you hear a train go past you, a train or a subway, you're just standing there. It just goes like, right? It gets louder the closer it gets to you, but the moment it starts leaving you, it gets quieter and quieter. So that's the way I like to think about it. So just think of it, if I had to say anything, think of trains. Might be a spoiler alert. You guys probably should have taken the AMC full length 2 by now. This is literally a question from it. So yeah, think of trains. Closer, it gets louder. Further, it gets quieter. Use this equation to figure out the frequencies or the velocities. So that being said, I think that's all I have for sound. We can move towards the last subject, which would be nuclear chemistry or half-lives. Now we know half-life is the time it takes for the concentration of a substance to go from its original to half. So it's the time for that. So alpha decay works in a way where you're releasing a helium atom, I believe. It's a helium atom. It's not. That's the way I learned it. You're basically, so if I use U38, 238, what is it, 92? If you release it, it's going to be 2, 3, 4, 90. I'm not sure what the molecule is, but you release a helium atom. If anybody's in the if anybody's in chat, you can look up what 234 is. That would be great. Or 90. Thorium? All right. Sweet, thanks, man. So yeah, it's thorium. You're just seeing that you're releasing a helium. You're losing 2 protons, so you're changing the element from one to another. Yeah, so I just know that you're releasing a helium. The helium will be present, so that's how you're gonna know it. Let's move on to beta decay. There's 2 different kinds of beta decay: beta minus and beta plus. In beta minus decay, it's you're basically releasing an electron. Or sorry, a proton. What would that would be barium. You're releasing a proton. They write it like this. I'm not sure, but like, honestly, I'll do you guys a favor and just write it as you're releasing a proton. And then for beta plus decay, you're releasing an electron and a proton. There's also a gamma decay, but you're just releasing a gamma particle. The general element will still be the exact same. That being said, I believe we are done with physics. I don't think I have anything else for you guys. Yeah, look at that, guys. We went through so much tonight. And you want to know the best part? We're not done. We have one more topic. We're going to have to go through organic chemistry. But I know you guys are tired. We just went through another unit, so we can cover... We can cover the basics of OChem. I'll say that we're taking a break. And I'll see you guys back in 5 minutes. Oh my god, that was so embarrassing. I can't believe you guys had to see that. Oh man, that one thing I hate about live streaming is that if you guys like, if I screw up, you guys see it in real time. Hope you guys enjoyed your break. Last one, fast one. We are going towards organic chemistry. So let's start off with organic chemistry. I wrote the SN1, SN2 stuff here. We can get started with that. These are the most basic reactions that you'll have to know. I'm erasing these because we already covered it. You guys probably won't ever see it again. So SN1, SN2. So SN1 has 2 steps. It starts where, so you basically kick off the leaving group, or the leaving group. You have a carbocation forming. However, it'll react it out, and then whatever your nucleophile is, this is step 1. Your nucleophile is present. In step 2, your nucleophile will attack this, forming your new product, which will be whatever the nucleophile is. So I want to state this prefers more substituents. It's like tertiary for secondary preferred over primary. Another thing is that it creates racemic products. And it can have a weak nucleophile. It can have a weak nucleophile. You guys know what nucleophiles, electrophiles, leaving groups, and all that stuff is, right? I don't have to cover that. Because that's very, very basic OChem. This is like, just like, I guess if I ever had to rename this, it would be foundations of OChem. Alright, well, I'll move on to SN2. SN2 only has one step. It's just Br plus whatever the nucleophile is, reacting with nucleophile. It attacks, kicks that off, basically forms that plus Br minus. So I realize I just used my space. It's okay. It's fine. I'm fine. Just know that it prefers less substituted carbons. So primary is preferred more than secondary, preferred more than tertiary. Methyls are also there, so methyls will be like the least preferred. But here it'd be the most preferred. Another thing, it doesn't perform a racemic product. It performs, it inverts stereochemistry. And it wants a very strong nucleophile for it to occur. All right, with that said, let's move on to isomers. This chart is honestly more than enough for your isomer stuff. One thing that I'd like for you guys to probably focus on would definitely be knowing your differences between your diastereomers and your enantiomers. Enantiomers are like non-superimposable mirror images, and diastereomers, they have multiple chiral centers. That's how you tell the difference between them. Yeah, I know I wrote that. I'm sorry, guys. Another thing with you guys probably know your chair conformation stuff, right? Like axial, equatorial. I'll go over that in a second, but I'm talking about like your ghost, your anti, your eclipse. You know which one's the lowest lowest energy and which one's like the highest energy, stable, and all that stuff. So that being said, these groups are called axial groups. These groups are called equatorial groups. And note that you usually would prefer to have equatorial groups over axial groups. Does anyone know why? Does it have something to do with steric strain? Sort of. It is strain, but it's not steric strain. It's called non-bonded strain. So non-bonded strain is when when the axial groups from two close by molecules, they sort of like overlap with each other. They start creating a lot of stress. They're nearby. You don't want that. You want it to be equatorial. You want to be able to you don't want a lot of meshing between molecules, if that makes sense. So that's why equatorial is usually preferred. But the most preferred, I will say, is having alternating equatorial and axial groups. Last thing I want to talk about is RS and E and Z. I'll start with E and Z first. So E and Z are basically like cis and trans. They are cis and trans. So E is associated with cis, or E is associated with trans, I'm sorry. Actually, I don't want to teach it to you guys like that. It's more like the more substituted groups are on opposite sides. So like opposite, same. That's a lame way to think about it. So is this, you see that the groups are on the same side, so this would be Z, but here they're on opposite sides, so that would be E. That's the way you think about E and Z isomers. R and S, I like R and S a lot more. The way I like to think about it is if you have, I'll just make a random molecule. Chiral center, so if we have put the H here just to make it easy for you guys. Why am I blanking? I'll do iodine, oxygen, and then a carbon chain here. So this is another carbon. You go based off of your periodic table. So the larger you have, the farther down you are on the periodic table, that's where the priority is given. So I would have priority number 1, followed by oxygen, who has priority 2. The carbon will have priority 3, so priority 4, and then you rotate in that direction to find out which one is R or S. Now, R or S, you can see the way I like to think of it. For R, right? R, you see that it's going this way, right? It will be going like that. S, it's written like that. I know it's complicated because you can say that it goes like that, but the way you write it would be like this. So they go in opposite directions. So you see it's going like that, right? So you see that? So this molecule will be an S compound. Now, one thing I'd like to point out is that if you have your hydrogen, which is the lowest priority compound, at the highest position, or if you have it pointing outwards, you would have to invert this. So it would actually end up being R that way. All right, cool. We got our basics of OChem. Let's move on to some other topics. Let me just see how much stuff we have left. Not a lot. We're fine, guys. Just hang in there. Redox reactions. These are very important reactions. I'm not going to go through every single reaction because I feel like OChem is very low yield, and I think we do know a lot of the stuff. It's just that like I'm going to go through stuff that's just very important. So I think the most important reaction, this is an oxidation one to form an aldehyde. So you would use PCC. That's the specific one they want you to know. And to form a ketone, this is for converting secondary alcohols. This a PCC specifically for primary alcohols, by the way. But for secondary, it'll be usually a chromate compound. So it can be doesn't necessarily have to be Na. It could also be potassium, lithium, whatever. But just know that it has to be a chromate compound. And if you want to reduce this to form an OH, you want to get rid of that, right? So I would recommend either LAH or I believe it is sodium borohydride. This is very strong though. I would point out that this is very strong. If you want to reduce it like a carboxylic acid, all the way down to an alcohol, you would use LAH. But if you want to just do ketone to alcohol, you could use the other one. Now, mesylates and tosylates. Mesylates, they have... I'll just say mesylates, they look like... Well, tosylates, they're a bit more complex. But they both do the same thing. They work to form a protecting group. Or they work to form a compound that works as a better leaving group for nucleophilic reactions. So as they make a better leaving group, they create a better carbocation. It makes it easier for the nucleophile to attach and basically just be a part of it. I was thinking of alcohol. So any alcohol that looks like this, anything like this is a very good protecting group. It works well with alcohols, it works well with carbonyls. So it'll just attach on, it'll form a protecting group, and then whenever you add more like hydronium or acid, you can just get rid of it and it'll be back to where it was before. Carboxylic acids. These... Oh, wow. I don't have a lot of space here. Okay, yeah, cool. So carboxylic acids, this is the basic structure of a carboxylic acid. I think I want to just jump right into the nucleophilic acyl substitution. This is like the backbone for every single like the derivative. So if you have an anhydride or an ester or anything like that, it'll basically be following that. I point on my screen like you guys can see. It'll basically just be following this this basic equation. So as you can see, it gets deprotonated. I didn't draw the nucleophile, that's why I'm confused. So when there's a nucleophile, it'll come here, pushing it out like this. That creates your OH here, the nucleophile is attached. And then when you add an H, you form that back again. It's like it attaches here, and then it causes the negative charge to go in, forcing out an OH. That's why you end up with this. So sorry, I was thinking of it differently. It doesn't attach here, it attaches here to form an OH2 positive, and the negative charge goes in, forming a double bond, kicking this part out. Now, with that being said, we have our new ketone with a new ketone compound. And if you want to reduce it to an alcohol, you would add another H+, and go here. Pushing this out, creating a negative, another one will come in, pushing it back in, pushing out the nucleophile, creating an aldehyde compound. You can add one more H+, it'll come in, push that out, causing an OH to form. Yeah, that's pretty much it. I know this is a bit messy. Carboxylic acids are a pretty tricky topic. They're not going to be tested that much in detail. If anything, you're probably going to see stuff about alcohols, but it's just still important to know. So with that being said, let's move on towards their derivatives. I want to talk specifically about formations. So anhydrides, they look like this, right? They're usually formed like in a way where it's something like this, yeah. No. Alright, yeah, that's my fault, guys. I'll save this, I'm gonna refresh. Alright, cool. So with the anhydride, this right here is going to be attacking the R group. Sorry, not the R group, I misdrew that. It's going to be targeting this, pushing this out, and then it'll create a negative charge here. That negative charge will come back here, basically pushing out the hydroxide group. So it'll form this. I knew I drew it a bit weird. I just wanted you guys to see what an anhydride looked like first. With esters, I wrote a bunch of trans esters, like ester stuff here. I should have written it here, but like I'll go with amides first. Amides, you can form it from either an ester or an anhydride. I think I'll start with anhydride since we just covered that. It'll be like this, plus NH3. And then we can see it as the NH3 will be attacking either carbon, neocarbon, forcing it out like that, creating a negative charge that'll eventually have to get pushed out through resonance. And it will create a product that's looking like this. And there we have it. We have our amine. It can also be formed from an ester, similar reaction. I'd say it's arguably easy because you know exactly where to go. So like if this was just an ester, you would just go here, take it out, it's coming out of that. I'll draw it for you guys actually. Plus NH3. It'll be like, it'll come here, come out, come back, lyse this, forming NH3. Sorry. With that being said, yeah, let's move on to transistor esterification. I think esters are the easiest for us to think about. So if we have it like this, and then if we have whatever alcohol, basically how you think it is. Exactly. Hydrolysis, similar thing. So the water comes here, pushes this out, pushes this back in, lyses this. There will be an OH, but then it'll be like deprotonated, so it'll form hydronium. And then reduction, last one. I'll use LAH. LAH will lyse this completely. It will reduce this to, so basically it just forms 2 alcohols. Oh, my bad. I should have, there we go. It lyses these completely, just forming 2 alcohols. So 1, 2, OH plus OH. I know this is pretty messy, but I think you guys can figure this out. I've done the nucleophilic acid thing over and over again. If anything, this is practice. So just make sure you guys know that. That being said, let's move on to our final topic, which would be chromatography and spectroscopy. I'll start off with chromatography. It's pretty straightforward. I think you just have to memorize all these, your mobile phases, your stationary phases. When in doubt, I'd say your mobile phase will be the nonpolar one. I don't want to cause bad habits though, but then again, you guys only have a few days left. That being said, memorize the chart. This should be more than enough. Let's move on towards spectroscopy. That's the meat of this topic. This is IR spectroscopy. And this is NMR, HNMR to be exact. I love IR spectroscopy. This is super easy in OChem. My favorite topic, mainly because I hated the rest of it, but that's besides the point. I'd like to point out that each functional group has its own peak, or in the case of the CH2 stretch, double peaks present on the chart. OH has a big stretch like that. The CH stretches have 2 double peaks here. This is like a fingerprint region. Usually you will never see anything here if I'm being honest. Carbonyl stretch. You guys can also just read these. Note that this right here, your highest IR specs you'll ever see will be in your amino groups. And HNMR, similar stuff. Each has everything for a functional group. I would like to point out that there is more shielding lower down, so your more complex molecules will be present here, while your less complex ones will be up there. and that will be warrants with having increased frequency or having a lower magnetic field. All right, I sort of sped through the OChem stuff, but there isn't that much I can really talk about. Is there anything you guys have questions about? No questions? All right, cool, guys. Well, we covered a lot today. Yeah, looking at like something like this, it is a lot. It's a bit messy, but it's a lot. Yeah, no, thank you all for staying, to the ones who stayed the entire night. Good job. I hope this covered everything you guys wanted to know. I'll end with just amino acids one last time. Yeah, so this is going to be my last lecture. I already said that I won't be doing a lecture on psychology because the Kaplan or the Khan Academy doc is more than enough. I hope you guys are covering that this week as a review. I can't really do much for you guys with cars. It's just you have to be good at reading, you have to be good at comprehension. But other than that, I did cover biochem, physics, and organic chemistry this lecture. I also covered general chemistry in a previous lecture and biology in the lecture before that. So I've touched all my bases for the MCAT for you guys. Your exam's coming up in a few days. Good luck to all the people taking on April 9th. And if you guys aren't taking it April 9th, you just came here to learn something. I hope you guys did learn something. I hope you guys like this like live stream setup. I really liked it. It was pretty fun just being able to like do something chill, hanging out with you guys. That being said, I've covered everything I wanted to. If you guys have any questions, leave comments. I'll answer it in the morning. That's all I have for you guys. I hope you guys have a great night. Good luck again to everybody taking it on April 9th. This was dedicated specifically for you guys.